Hello, beloved Shirtloads listeners, Dr. Karl here. Welcome to some excellent repeat episodes. You see, I'm on sabbatical overseas, and I'm working on a strategy using artificial intelligence to counter climate change disinformation. Ooh, big topic. So stay tuned for updates about this exciting new project. But in the meantime, enjoy these next few episodes covering dark matter, healthy eating for families, and wait for it, growing eardrums. I'll be back with new episodes and maybe a new AI chatbot in late April. Catch you then.
G'day, Dr Karl, University of Sydney, Shirtloads of Science. And today I have Dr Ellen Sirks.
Perfect.
And how many languages do you speak?
2 fluently, Dutch, which is my mother tongue because I'm from the Netherlands, and English. I know a little bit of German and French and things like that.
You were involved with searching for 25% of the universe that we can't find, or 20% or something like that, the dark matter, and you still are. And there was a big adventure with a balloon that you put up and you couldn't get data and people had to go searching through jungles. And
very exciting.
Very exciting. So Dr Ellen Sirks, S-I-R-K-S.
Yeah, I'm an astronomer, or cosmologist is probably the right term, but I kind of changed which term I used.
Okay, so there was a big adventure with putting up a balloon and then trying to rescue it from the jungles, and it was to do with dark matter. So can you explain dark matter?
Sure. There's 2 types of matter in the universe. One type is the type that we all know of. We call it ordinary matter.
Regular.
Yeah, regular matter, or baryonic matter is the proper particle physics term.
Oh, really?
Yeah.
But you deal with a very big, like astronomy, and you talk with the people who deal with the very small, like the particle physicists.
I know. I'm actually in the astroparticle group at the University of Sydney, so I'm kind of the best of both worlds, really.
Isn't that interesting that you're marrying stuff much smaller than an atom with stuff much bigger than galaxies?
In my opinion, that's how we're going to solve the mystery of dark matter, because eventually, if it is a particle physicists should be able to find it, and it should be consistent with what we see in the universe. So
you've just hinted that there is this stuff called dark matter, which is not like regular baryonic ordinary atom, which is that made of atoms, that stuff?
The ordinary matter is, amongst other things.
And looking at the whole universe, the numbers I've kind of heard are 70-something% is dark energy.
That's right.
Roughly, ballpark. 4 or 5% roughly is regular matter.
That's right.
So 20-something, 25% is dark matter.
Yes, that's right.
25% of the universe is dark matter.
So about 5 to 6 times more dark matter than there is ordinary matter.
What makes us think that it exists?
This is how science works, right? You look at something, you don't understand why it's happening, and you try to figure out what is happening. So we look at the universe, we see things that cannot be explained by there just being ordinary matter. For example, one of the earliest publications or thoughts about dark matter was in the 1930s by Fritz Zwicky.
The man who made up that wonderful insult of that person is a spherical bastard.
Oh, really? I've never heard that one before.
So that meant that whichever way you looked at that person, they had no redeeming features.
Oh, dear.
Every way they were bad.
Very smart.
Brilliant.
Yes.
And so Zwicky did what?
He looked at a galaxy cluster, which is a group of about 100 to thousands of galaxies, so huge. And in particular, he looked at the Coma cluster. And what he found was that the galaxies in that cluster moved a lot faster than they should if there was only normal matter, so only stars and gas in these galaxies.
Okay, so we've got a bunch of galaxies. Each galaxy is, in the case of our galaxy, 300 or 400,000 million stars. They can be bigger, they can be smaller. These galaxies come in different sizes, and they're all orbiting their common centre of gravity, like a bunch of angry bees buzzing around, orbiting their common centre of gravity. And what did he find?
They were moving a lot faster than they should.
They should fly away because they were moving too fast for the mass that he could see.
Yeah, so you can do a fairly simple calculation just using Newton's gravitational laws, and it has the mass of your galaxies, the mass of the whole system, the distance between those two things, and something called the gravitational constant, which is not super important. And by comparing those things, he found there was a really large discrepancy in the velocity. And another way you could translate that is that there was a large discrepancy between the mass that was actually in the system and the mass that he could see. Because, if you know a little bit of what a sort of average galaxy, how heavy that is, you can make kind of an estimate of the total mass of a galaxy cluster if there's only galaxies in it with no dark matter.
Only stars in the galaxy.
Yeah.
Didn't another scientist look at rotating of galaxies? Now, who was that?
Vera Rubin.
And she's getting a satellite or telescope named after her.
Yeah, as she said, because she's absolutely brilliant.
Oh, so what did she do?
A very similar calculation, but on a smaller scale. So she looked at something called a rotation curve.
Rotation curve.
Of a galaxy, which is where you look at how fast stars in a galaxy are rotating as a function of their distance from the center of a galaxy.
In the case of our solar system, where most of the mass is in the centre, Mercury, really close, is doing, say, 60 kilometres a second, something. Earth, 30 kilometres a second. Poor old Pluto, which I still think should be a planet, is doing only 4. As you move further out, the speed slows down, and she didn't find that.
Yeah, so if you just use, again, like these sort of basic gravitational laws, what you should find is that it increases a little bit from the center, and then as you move away, it sort of starts decreasing again until there's nothing, no matter anymore. But instead what they found is that there wasn't this sharp decrease, it sort of remained flat, which indicated again that there had to be something that was keeping this galaxy together, that was keeping these stars rotating.
So Zwicky looked at a bunch of galaxies orbiting their common centre of gravity. Rubin looked at one galaxy, and as you're staring at it, and it's rotating, one side's going away from you, one's coming towards you, so you can measure the velocities. And you can also measure the velocities across the galaxy from left to right. And what did she find?
As you go further away from the center, that instead of the velocity curve falling off, so decreasing, it was more or less remaining flat for a lot longer.
In our solar system, the velocity drops. Mercury, then Earth, then Pluto, but here it was pretty well constant.
Yeah, so there had to be something else. Again, or another way of thinking about it is that all these stars should be flying away. If they were moving that fast, they shouldn't be able to keep that galaxy together.
You're a working scientist involved with building Superbit?
Yes, that's right. Astronomers love weird acronyms, and this is no exception. So Superbit stands for super pressure. So that's the super part in Superbit.
Super pressure.
Yeah.
Okay, we'll worry about the pressure later.
Sure.
Yep.
And then BIT is balloon-borne imaging telescope.
So it's BIT.
That's right. But we just spell it BIT.
Imaging telescope. How big is the mirror?
It's a half-meter telescope.
There are bigger mirrors and smaller mirrors, but I'm guessing you're focusing on special targets. Here, we'll get to that. And then visible or ultraviolet?
Yeah, so we're operating mainly in the optical, from about 300 to 900 nanometers. So what we can see with the naked eye.
And a little bit of extra ultraviolet, a little bit of infrared.
Near UV to near infrared.
So this telescope is up there. Where is it?
33 kilometers or 100,000 feet.
So either you've got a very long, skinny building or you've got a big balloon.
A big balloon, yeah. A super pressure balloon.
So that's a super. Have you seen one of these launched? Can you describe it for us?
I did see it live on cam, but there was a test flight in 2019 where I was also present. I did see the launch and it was amazing.
I've seen a launch from Alice Springs and we had to get up early in the morning and then just hang around. And then they decided, okay, the weather's going to be fine. And then they laid out this canvas about a third of a kilometre long.
Yeah, it was very big.
And then on the canvas, they roll out the balloon, which has been carefully rolled inside, and they unfold it. And so you've got this long, skinny thing about a fifth or a third of a kilometre long. And the wall thickness is thinner than cling wrap or something, incredibly thin. 2 trucks turned up, semi-trailers, full of cylinders of helium, and then 2 men who were chosen mainly for their weight hung onto these big tubes the diameter of a human thigh.
Sure.
And then they hung onto it for a couple of hours while the helium gas just flooded into this balloon and it started to lift at one end like a little teardrop. You had to have zero wind because if it was partially inflated, the wind would blow it. That stuff thinner than cling wrap would go across the grass and it would deflate and it'd die, and you'd just wasted a couple of $100,000.
You have to be very careful with these.
So you saw it actually begin to inflate?
In 2019, I did, yes. I saw the whole thing.
But did you get excited inside and think, oh my God, it might actually take off?
Yeah, I mean, it was amazing. We're a relatively small team, like 10 to 20 people. And then we also have sort of the NASA operations crew that helps us. But we were all, screaming like it was a concert or something.
It's amazing, isn't it?
Yeah, it was one of the best things I've ever seen.
And
in
it
my
started
life.
to get bigger and bigger?
It starts to inflate and then very slowly starts to lift and lift until it's above the telescope and then...
Oh, so the whole thing goes above the telescope. So you've got this long, skinny, like a thin candle?
It inflates once it lifts the telescope up and it gets higher and higher in the atmosphere. And eventually it gets really big.
So it begins to go sideways. Mm-hmm. How big can it get?
I've heard some funny measurements. The best one I've heard is that it's about the size of a football stadium when it's fully inflated.
A couple of 100 metres across.
Yeah, so it's huge.
Because I remember we were driving into Alice Springs. We'd just come across the Simpson Desert and we were going there for a balloon launch, and we saw it in the sky from 50 kilometres away, a previous launch.
Yeah, so you can see it from very far away.
See it. It was huge and the air was clear. So you saw the balloon began to spread sideways, and I think the big moment is when it's able to lift the gondola off the ground.
During the test launch, we had another smaller balloon levitate the telescope above the ground so that it was sort of already up and wouldn't scrape and things like that.
Yep.
During this launch, we didn't have that. So basically, it was hanging on a crane.
Oh, God.
The balloon would get inflated and slowly go up. And when it was right above the telescope, the crane operator would pull the plug, release it, and there up it went.
The higher it goes, the less the surrounding pressure, so it begins to inflate.
Exactly,
more.
yeah.
But the tension during that launch, that if there's the slightest bit of wind, it's so big, just a breath of wind will blow it across the grass and it just bursts open. So, okay, so you got your balloon up and it goes up to 33 kilometres, 100,000 feet or whatever unit they use. Did it go and stay there or go around the world? Was it in the northern hemisphere, the southern?
We operate on the southern hemisphere.
Yeah, of course, because we got the best sky.
Yeah, that's what we say. And it went around the world about 5.5 times.
Hang on, it went around the world 5.5 times at 100,000 feet. So I'm guessing you launched it from New Zealand, it would have kind of stayed roughly there-ish. It wouldn't have gone towards the equator and gone to the other side. So it would have stayed down south.
If anything, it went a bit more south, if I remember correctly, yeah.
Is there the danger that if it goes too far south, that it then would land where there's no land and drop in the ocean and then you've lost it?
If it starts spiraling in south, it's very hard to use the solar panels to get energy, and eventually you'll just lose
solar panels.
Power, yeah.
So you've got to have power for it as well if it goes too far south. Obviously, there's not a big sign saying, hey, you have found your dark matter. Congratulations, pick up your Nobel Prize.
Woohoo! Well, the thing is, we know where the dark matter is, more or less. We just don't know what it is.
Where is it?
All over, really.
But is it clumped or is it smooth?
That's a question that we're trying to answer, right? So we know more or less what objects we want to look at to study dark matter.
Yep.
But we need to study them to sort of figure out what the properties of this mysterious matter is. We look for dark matter using something called gravitational lensing.
Gravitational lensing. So
yes.
There was a guy, John Wheeler at University of Texas at Austin, said, mass tells space how to curve. Mass follows that curved space.
Yeah.
So light will also follow that curved
exactly.
space. Space is curved and light will follow that curve. So what is this strong gravitational lensing then?
Gravitational lensing is the phenomenon that you describe where the light from a certain object gets bent as it moves past a massive object.
So light gets bent. That must have been so hard for people to believe.
When I first heard about this in my undergrad, I was like, that sounds like some science fiction story. I don't believe it, but
Einstein said it and it's been proved a zillion times.
Einstein said it. Gravitational lensing is also predicted by Newtonian gravity. It's
You're
more,
kidding.
Yeah, it is. It's more the magnitude of the lensing. That's different. There's a really great movie, if you're interested in how this works, called Einstein and Eddington or something like that, because Eddington is the astronomer that helped Einstein gain traction that general relativity
by
was
looking at the eclipse thingy.
Anyway.
So with strong gravitational lensing, mass, whether it's dark matter or regular matter, will make light curve. So give me an example of Einstein lensing.
One of the coolest one is called an Einstein ring.
Einstein ring.
Yeah, so that's what happens when you have, for example, a galaxy that's directly behind a massive object that does the lens.
Oh, so you got three objects in a row. Us with our telescope, and then
the lens,
the lens, which is a massive galaxy.
Yeah, just massive object.
Because it's got mass, it'll curve space, and then directly in a straight line behind it, you got something else, which might be
a galaxy.
A galaxy.
Yeah.
Okay, but they're in a dead straight line. What do you see?
You get this beautiful, perfect ring around the lens. Yeah, so you see a ring in the sky.
A ring.
It's beautiful, yeah.
If you get it exactly lined up, do you get? Have you ever seen like a perfect ring, which is equal brightness all the way around the full 360?
Pretty close. It exists. I mean, for a perfect ring, it has to be perfectly aligned. The lens has to be perfectly spherical. The object itself has to be perfectly uniform in light. So all these things don't really happen in nature, not perfectly at least.
By the way, loyal listeners, just then you heard the brain of a physicist answering a question.
Oh, really?
Yeah, that was good. So instead of just seeing like a nice galaxy like two soup plates stuck together with hundreds of thousands of little points, you get a ring. The whole image gets smeared, and that's a strong gravitational lens. But with superbit on your telescope, going 5.5 times around the world with unproven brand new technology that you are building. So you're a theoretician and an experimentalist to some degree?
Sometimes a little hard to define exactly what I am. Sometimes that's observational astronomy. Sometimes it's more theoretical. Sometimes, in this case, it's more electrical engineering almost.
You did electrical engineering?
A little bit.
Yeah. So forget strong gravitational lensing. You're using weak gravitational lensing. So we're relying on the fact that matter, and it doesn't have to be regular matter, it can be dark matter, can make light bend. So what is this weak gravitational lensing that you're looking for with superbit?
Strong lensing is when the distortions are visible. Is more or less the definition.
Like,
and weak,
like visible to
the naked eye, almost.
Or you look at the image and you say, yeah, that's some lensing.
You're like, clearly this is not an actual object in the universe. We don't really know of ring structure that perfectly shine that way.
Or sometimes you can get like multiple images of the same galaxy.
Exactly, and perfect twins of galaxies. You can tell that can't be.
So that's strong. Now tell us about weak.
Most people haven't, but we use it a lot, especially to study dark matter.
Why wasn't I told? Why didn't I get the email? Okay.
Exactly. So weak lensing, it's the same phenomenon, gravitational lensing, except in this case the distortions are not visible. But because, for example, a group of galaxies behind the lens, they more or less experience the same bending of the object that's in between us and these galaxies.
Yep.
They have an almost systematic alignment with this bending. So they have a distortion that's impossible to see. But if you do a statistical measurement of these galaxies' shapes, you should find that they're slightly turned in the same way, if that makes sense.
Oh my God. Let me try and put this back to you and you tell me how wrong I am. If you've got a bunch of galaxies in the sky, are you looking at an individual galaxy or a bunch of galaxies?
A bunch of galaxies. So it's a statistical measurement. So you need to have lots of galaxies to be able to tease out this information.
And how many galaxies would there be in a frame? Like 1 or 10 or 100 or 1,000 or 10,000?
That depends a little bit on how good your telescope is.
The superbit 1/2 meter one?
It's somewhere between 20 to 40 galaxies per square arc minute, which is this unit that we use in astronomy.
There's a bit of sky. I've got my telescope, my superbit telescope. I happen to be up there 100,000 feet above the ground wearing my spacesuit. I aim it at a bunch of galaxies and I go click, 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 and there's no dark matter in a way, and I get a certain pattern. And then I look at another bit of sky and there's a lot of dark matter in a way, and I get a slightly different pattern.
Galaxies are not perfectly circular objects. They're elliptical, they have different shapes, and so they have an intrinsic shape to them, even if there's nothing doing the lensing. But if there's something doing the lensing, all these differently shaped galaxies should have a distortion that's kind of in the same direction, because they're being lensed by the same object, if they're in a sort of similar location. And so this is really hard to do. You know, you need to have the shapes very precisely in order to get this information. And so it's a difficult measurement to do, but if you can do it, you can tell more or less where the dark matter is and try to study it.
Wow.
Like
so this is what you're working on now. Now, apparently there was a big adventure and things went wrong. So tell us about what went wrong and how people had to go running through the jungle fighting off dinosaurs with their bare machetes or something. Okay, so tell us a story.
When one of these telescopes come down, it's always, a rough landing. These telescopes never remain whole. You can't just pick it back up and put it back up. That's always the case. Okay. Especially because these telescopes they need to be so clean and the mirrors need to be so smooth.
So it's not going to come down and kiss the ground with zero velocity in a perfect horizon. It's going to scrape across the ground.
Well, scrape across the ground, preferably not, except that is exactly what happened in this case.
Where did it do this?
Patagonia in Argentina.
So we're talking about very southern part of the world, almost so far south that if you go a bit further south, you're in the Antarctic. Did you deliberately land it?
Yeah, we can decide when to start the landing procedure. That's right. And on a parachute.
Vent the gas, and it comes down on a parachute, does it?
Yeah. So
from 33 kilometers up.
Yeah.
Wow.
The problem in this case was that when you're close to the ground, the parachute should detach.
Yep.
When it was supposed to have detached, it remained attached to the telescope, and so it sort of got dragged along the hillside for a couple kilometers, the telescope.
In Patagonia?
Very rough and hilly and lots of stones. So it's not the softest landing, and especially in this case.
Once it makes impact, it's supposed to dump the parachute, and it didn't. Or were there things going wrong with it?
They have this software to predict where the telescope goes according to the weather forecast, and they were worried that for the next few weeks it was never going to go over land again. It was just going to slowly spiral inwards towards Antarctica. And if that happened, it would be extremely difficult to retrieve any of the parts of the telescope.
Oh, because you built some stuff, didn't you? The data on terabyte hard drives, and your data transmission rate was too slow to send it down.
Normally, when you have these type of experiments, you want to retrieve data mid-flight,
Yep.
sort of to mitigate the risk of losing all your data in case the
Sure.
telescope crashes somewhere, And the way you would ordinarily do this is via satellite.
Send it up to a satellite.
And then we sort of download it.
Right.
We found that in our case, we were getting so much data per night. It was like 20 gigs per night or something like that, that it would take too long and it would be too expensive on the Southern Hemisphere in this case. We decided we have to do something else. Why don't we just download it onto an SD card?
So you go to your local stationery shop and buy an SD card.
They don't tend to be as spacious as the ones that we wanted.
So you got big ones that
1
were top of the
terabyte ones.
grade and
Yep.
high speed.
And so we download the data onto these SD cards, and they are loaded into something called a Raspberry Pi, which is this sort of...
those little baby computers.
Yeah, that everybody can get. I would recommend people do so because they're really fun to play around with. We have this little Raspberry Pi that's attached to a circuit board, and then the circuit board has these two things called archery releases. If you know about professional archery, in my understanding, it's what these sort of pincers that hold the line taut.
So this is a bit of technology you found.
Yeah.
Wow, neato.
I know,
Wow,
isn't
I
it
had no
amazing?
idea. I had no idea it existed.
Isn't it great?
Yeah.
And so these archery releases are attached to a parachute and a tether that goes to the telescope. And then basically, once you've downloaded the data onto this SD card, from the ground we say, we want to retrieve the data now. One of these archery releases that holds the thing to the telescope opens. The whole thing comes down to the ground, floats down on a parachute, and you can pick it up.
In a different place.
Yeah, wherever you want.
But is it the same where the telescope lands, or is it...
If you want to.
And so what happened here?
Because the decision to terminate the mission came a bit sooner than expected, and so we hadn't dropped any of these data release packages that we made, but we wanted to test them, and we wanted to make sure that our data came back. We had 4 of these packages, and each of them had all the data we'd taken on them, as well as the onboard computer of the telescope had all the data on them. It's more redundancy. And so we dropped 2 right before the telescope was brought down. So they came down some distance away from where the telescope
Did
eventually
they
came
fall
down.
all the way from 33 kilometres down?
That's right.
So the telescope is still up there, and you say, see you later, guys, and you just boot them out, and then they
Yeah.
fall out on parachutes.
Yeah, sometimes the simplest things work the best.
How do you track it?
A lot of countries don't like it when you just drop stuff.
I know.
Right, isn't it
they
so
get
annoying?
That way. Annoying.
So there were a lot of safety requirements that we have to meet. One of them was that we have to be able to predict more or less where these packages land, depending on when and where you drop them. I wrote this software that does these predictions. So you give it an initial time and date, a location, latitude, longitude, altitude, and then it predicts where this package lands. And so we had to run those to see, does it land in a safe area, no population, things like that. And 2, in an area that we could actually pick it up from. So preferably not a forest, preferably not a lake. And if we can, near a road. It has an antenna, it has a GPS tracker. So it is able to send us its location as it's falling down. I actually get emails in my inbox. Hello, I'm at this altitude and at this latitude and
cool.
longitude. Yeah.
Your colleagues had to go into the wild
That's
and
right,
rescue
yeah.
this. And so how much data do you have?
Loads.
Enough to get you a Nobel Prize, or are you just building up a small part of it? Have you analysed any of this stuff yet?
A lot of these data, they're what we call raw images. They still need to be cleaned. For example, there might be satellite streaks or cosmic rays and things like that. And all these things you have to sort of clean before the data is ready for science analysis.
Further down the line, you will get a statistical analysis, a hint as to the possible distribution of dark matter.
That's right. We'll be publishing papers on that relatively soon, where we're actually doing stuff with our data.
Well, loyal listeners, if you want to get into, what is it?
I would call this more observational astronomy. I'm more an astroparticle physicist at the moment.
I've never met an astroparticle physicist, so hello. Suppose people want to get into this field. How can they contact you and follow you in your fine work?
Find me on ResearchGate. So my
that's
papers and published work are on there.
ELLENSI for India, RKS.
That's right. I'm on LinkedIn. I have a staff profile on the University of Sydney with my email address. So send me an email if you want more information.
Wow, thank you for taking me on this exciting journey.
Well, thanks for having me and coming along.
And thank you for explaining weak gravitational lensing. I had no idea that such a thing existed.
It's fascinating.
That's the thing I love about astronomy. It's so fascinating.
Me too.
Shirtloads of Science is washed, spun and aired by the University of Sydney. I'm Dr Karl, coming to you from the lands of the Gadigal people of the Eora Nation. I acknowledge Aboriginal and Torres Strait Islander peoples as the first Australians and traditional custodians of the lands where we live, learn and work.